So way back in 1999, NASA lost the Mars Climate Orbiter, $125 million spaceship. It went out to circle Mars, orbit Mars, and it got too close and got pulled in and crashed up. And the cause of that was found to be a miscommunication about units. Some people on the team were doing calculations in inches, and some were doing it in centimeters, and they didn't specify. And so when they programmed the thing to adjust its orbit, they used the wrong unit and lost the whole spaceship. Units are important. Now, we're not going to have any consequences like that, but there are lots and lots of ways where leaving out units is going to cause problems. So we need to understand what units are and how they work, and then we need to include them. Anytime we have units, we should be including them in our equations. So what is a unit? A unit is a standard quantity used to specify measurement. And when you stop and think about it, all units are just made up, right? Why is a foot a foot? Well, originally it was the length of the king's foot. And so then you got some trouble when the next king has smaller feet. We lost our standard, we have to change everything. So they eventually realized, maybe we should this is the foot, we'll just stick with it now. But there are different systems of units. And the two most common ones are the metric system and the English system, is sometimes called the imperial system. The metric system is used in most of the world, and here in the United States, we're very stubborn and insist on keeping the English system, which is a little ironic considering we fought so hard to free ourselves from the English, right? But we're keeping their measurement system. They don't even use it much anymore, but it doesn't have to make sense, I guess. The unit system that scientists use is the International System of Units, abbreviated SI, from the French for International System of Units. It is based on the metric system. For all intents and purposes, there's no difference. The differences are very, very small, basically about what is the base unit for this quantity. For mass, it's gram in one and kilogram in the other. Other than that, really doesn't matter. So I will use metric system and SI system pretty much interchangeably. And I will not ask you what the difference is. So these are quantities that can be measured, and the units that are used in the SI system. So length is measured with meters, mass with kilograms, time with seconds, and that's the same second that's on the second hand of your clock. Temperature is measured in kelvins. Amount of substance is measured in moles. These last two we don't care about in Chem 1A. We have symbols or abbreviations for these units. That saves us, we can write lowercase k, lowercase g, instead of writing out kilogram. It saves time, right? But in order for that to work, we have to agree on what the abbreviation is, and I'll use it in the same way. And there's some letters like K that show up in different places. Like here, capital K is the Kelvin temperature unit, and the lowercase k here is a metric prefix, kilo meaning 1,000. So it's important to be precise with your symbols. I'm going to go through this kind of quickly. You should know what is measured by the different base units and have some ballpark idea of how big they are. So the meter is used to measure length. It's slightly longer than a yard. This is a meter stick. It's 1 meter long. It's 39.5 inches long. It's not a yardstick. We were cleaning out our house and we found a yardstick. Right? It's like, oh, you never see those anymore. They're all meter sticks. So about a yard. So human is about 2 meters tall. So if somebody tells you that basketball player is 7 meters tall, that's ridiculous, right? It's just not possible. 7 feet? Sure, no problem. But not meters. Mass is measured in grams or kilograms. In chemistry, we often use grams because we're measuring smaller quantities than a kilogram. A kilogram is about 2 pounds. And this is a measure of mass. Mass is the quantity of matter. The weight of an object measures gravitational pull. And so your weight on Earth and your weight on the moon are not the same. But your mass is the same. So as long as we're all staying on the planet this semester, we really don't need to worry about the difference between mass and weight. We kind of end up using them interchangeably, but they're not exactly the same thing. So the gram is what we use in chemistry. A gram is 1/1000th of a kilogram. Another way to, just keep a ballpark idea. A nickel, which is 5 cents, weighs about 5 grams. So that's a small amount. Second, we know what that is. The definitions of all of these things have changed a little bit over the years because we need to define them very, very precisely. And so it's now defined as the period of time it takes for 9,192,631,770 periods of the radiation emitted from a certain transition in a cesium-133 atom. Yeah, not going to test you on that. It's just kind of fun to say that long one. Temperature. So in science, we use the Kelvin. Temperature is a measure of thermal energy, the average kinetic energy of atoms or molecules. Temperature can also tell us what direction thermal energy is going to transfer. Energy always flows from the warmer thing to the colder thing. And that's what we typically call heat, when it transfers from one to the other. So the thermal energy transfers from hot objects to cold objects. There are 2 other temperature scales that are used as well. The Fahrenheit scale is used in the U.S. And so you hear the weatherman saying it's going to be 95 degrees today. He means degrees Fahrenheit. Okay. The origin of this temperature scale has a whole long story to it. But as with many English units, it has kind of a random history. And so on the Fahrenheit scale, water freezes at 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. Those are kind of random numbers, aren't they? The metric system is based on multiples of 10, which once you get the hang of it, makes it so much easier. The Celsius scale is a metric scale, meaning it's based on tens. And so this scale is based on water freezing at 0 degrees Celsius and boiling at 100 degrees Celsius. Because you think about it, you're going to make a thermometer. At some point, you have to pick a temperature and give it a name, right? So boiling water and freezing water are easy to make, right? And these were all determined long before electricity and stuff. And, they didn't have thermocouples and fancy electronic stuff, right? So how do you calibrate your thermometer? You stick it in freezing water and you make a mark. Okay, that's 0. You stick it in boiling. Oh, that's 100. And then you divide it into 100 pieces. And you've got your thermometer. Both of these can have negative temperatures. You can have temperatures that are less than 0. On the Kelvin scale, we have an absolute 0. It's not possible to go below 0. So what's similar about the Celsius and the Kelvin scale is the change in temperature between boiling and freezing of water is 100 units. The difference between these is where is 0. Here, 0 is marked at the freezing point of water. Here, it's at absolute 0. What is absolute 0? Absolute 0 would be the temperature at which the motion of molecules and atoms stops. Because temperature is the kinetic energy, the thermal kinetic energy of the wiggling molecules. So as they get colder and colder, they slow down and slow down and slow down. And when they're acting like they're dead, they're not moving at all, that would be 0. Can't get colder than that. So there are two formulas that we're going to use to convert temperatures. And I think if you look at the useful information for exam 1, I think I give you these on the exam. Can't quite be sure of that. But you do need to know how to convert between Celsius and Fahrenheit. The Celsius Fahrenheit is kind of messy because it, bless you, involves subtracting and dividing, and so it's a little bit messy. Kelvin and Celsius is easier because you just have to offset the 0. So you take the Celsius and you add 273.15, that gives you the Kelvin temperature. So let's practice one of these. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. Sounds like it would be fun to play with, huh? It's kind of toxic, so can't do that. Kind of like mercury. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and the Kelvin scale? This is what, when I was growing up, we called these story problems, which I think sounds much friendlier than word problems. Right? It's a story. They're telling us a story. Isn't that nice? Yeah, and there's numbers in there, and then you have to do math. So most of these words are just there for the story. We want to pick out the numbers because that's what we're going to need to use. So here we've got 85 degrees, 85.6 degrees Fahrenheit, and we want to know what that is in Celsius and Kelvin. We can change Fahrenheit to Celsius, but changing it to Kelvin would be very messy. We're not even going to try. We're just going to go from Fahrenheit to Celsius and then change from Celsius to Kelvin. So we need an equation for this. So degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. So we can plug our number in here, the temperature in Fahrenheit, 85.6. We're going to subtract 32, and we're going to divide by 1.8. Now, it's easy to make a mistake on your calculator here. You need to tell your calculator to finish the subtraction before it does the division. Otherwise, it's going to do the PEMDAS thing, and you're going to end up with 85.6 minus 32 over 1.8, which is not right. So a lot of times we'll put parentheses up here just to kind of emphasize it. There's different ways to do this on your calculator. Get your calculator out. You should have brought it. If not, you'll remember next time. You can use the parentheses. Most calculators now have parentheses. If that works for you, you go right ahead. Put the parentheses in there. Everything will be good. Some people don't like to push more buttons, right? So you can also do 85.6 minus 32, and then to force your calculate to finish that, you press equals or enter. So mine now says 53.6. That's the difference in the numerator. Now I'm going to divide by 1.8, and I get this messy number, 27.777777777. 77 repeating. Celsius. So when I do calculations like this, I want you to be doing it on your calculator too, because sometimes your calculator misbehaves. And if it's not doing what it's supposed to do, you can ask me and I'll come over and give it a little lecture and make it shape up. Because it's always the calculator's fault. It's not your fault, right? But you don't know that it's misbehaving until you get home then, and then it's harder to get help. So it's always a good idea. Another reason to do the calculations is I make mistakes. And it can be really fun to catch the teacher making a mistake on a math problem, right? And I want you to do that because I've had lectures, I put these up on YouTube, and people from, not a lot of people, but a few people from all over the world see them, and sometimes there's a mistake on there, and the students didn't tell me until like the next day. And I'm like, dang, I don't want to go back and fix that. You know, this is embarrassing when somebody on YouTube 2 years later says, hey, you did your math wrong. So check my work, right? Follow along. So the book doesn't know that we skipped ahead and learned about significant figures. This is one of those sig fig things where we have the two different rules. And so it requires more thinking. But I have a shortcut for you. So for temperatures, just look at what decimal place does the original measurement go to. Here it's got 1 decimal place. Whether you're any of these conversions that you're doing, round the converted number to the same decimal place. So we want to keep this one at 1 decimal place, so we would call that 29.8 degrees Celsius. Not a big deal, but we should at least try. So that's the Celsius temperature. And then to convert that temperature to Kelvin, we can't start with Fahrenheit. We'll need to start with the Celsius scale. And it's best not to use a rounded number, so we're going to use this one. So Kelvin is equal to the temperature in Celsius plus 273.15. So 29.777, etc., plus 273.15. 302. I didn't mean to do that. 0.9277 repeating. The original measurement had 1 decimal place. We're just going to round our answer to 1 decimal place and call this 302.9 Kelvin. You can also use the sig fig rules, but most students don't want to do that. And if you're very curious about how can you just do that, I'll be happy to explain it to you later. Any questions? This is the conversion that we do a lot, because I've actually never seen a thermometer with kelvins on it. They're all Celsius. But when we do gas laws, we have to convert to Kelvin. So we're converting to Kelvin a lot. And those are the answers, and yay, I got the same answers. So scientific notation, and there's an appendix in your textbook that will help you review that. There's also a study module in Mastering Chemistry that'll help you to review scientific notation. We're going to use scientific notation a lot. Scientific notation lets us take really, really large or really, really small numbers and express them conveniently by factoring out tens. So, times 10 to the 23, we factored, 10 to the third is what I meant to say. Times 10 to the third, I've factored out 3 tens. Divide by 10, divide by 10, divide by 10. And that makes the number easier to look at and easier to punch into your calculator. The metric system uses prefix multipliers to change the size of the units. Those are also factors of 10. We need different sized units, right? I live in Reedley and I teach here in Fresno, right? So how far is it to my house? What kind of a unit would I use? Miles maybe, or kilometers? Would I tell you in inches? I could tell you in inches. Would it be meaningful? No, it wouldn't. We want the size of the unit to be close to the size of the thing that we're measuring. So we need lots of different sizes. So in the metric system, the prefix just changes the size of the unit by factors of 10. So the prefix kilo means 10 to the 3, or you could think of it as times 10 to the 3. So 1 kilometer is 1 times 10 to the 3 meters. When we're reporting a measurement, we'd prefer to choose a prefix that's close to the size of the quantity that you're measuring. And that's what a couple of those questions, I think 2 and 3 on the worksheet, have to do with playing around with powers of 10 and metric prefixes. These are a lot of the metric prefixes. I put some of them on your memorization quiz. The ones you really should know are kilo, centi, and milli. Those are the 3 big ones. And after that, I'd say micro, mega, and maybe nano. That's not what I meant to do. Sometimes you look at all the stuff somebody's asking you to do and you're like, I can't do all of that. Instead of just doing none, do some, right? Some is better than none. So if you don't have whatever it is needed, time, energy, willingness, you all have the brains, if you're not going to memorize all of the ones on the memorization list, memorize those 3. And that'll get you through a lot of stuff, okay? So here we have a measurement, 4.5, capital M, lowercase m. Lowercase m is meter. Capital M is in here. Capital M is mega. There's actually 3 M's, and we run out of, so we have the capital M, we have the lowercase m, which if it's in front of something else, it means milli. If it's all by itself, it means meter. Sorry, I know that's a little confusing. And then the prefix micro also starts with an M. We didn't have any more English M's or, what is that alphabet? It's not just English. Anyway, we use the Greek alphabet. So Greek micro. So there's 3 of them with M's. But here we have capital M. Capital M is the big one. It's mega. So if we haven't memorized it, we can look up in the table and see the capital M stands for 10 to the 6. Basically it means a million. So what we can do, how long is this in meters? Well, 4.5, instead of writing the prefix, I'm going to write what it means. It means times 10 to the 6 meters. And that's what it's asking you to do in the worksheet. And then this one is saying 7.13 times 10 to the minus 9 liters is equivalent to how many nanoliters? Well, what does nano stand for? 10 to the negative 9. Nano, nino, kind of go together. So what we're going to do here is, instead of writing 10 to the minus 9, we're going to write nano. 7.13 nanoliters. Any questions? Yeah.
Are we going to do conversion
very soon. Tonight. Yep. Any other questions? There are also derived units, which are combinations of other units, not just length. So if we have volume is a measure of three-dimensional space, and so we have units for that. This is a cubic meter. That is me. That is me. I got to go to Oslo with my sister-in-law a few years ago and went to they have a science museum, and they have this 1 meter cube that you can sit in. And it's like, oh, cool. I got to take a picture of that and use that in my PowerPoint slides. But that's how big a cubic meter is. It's pretty big. I wouldn't want to live in that, but you can sit in there very, very comfortably. It is 1 meter wide, 1 meter tall, and 1 meter deep. Right? Remember, geometry, length times width times height equals volume. So when you multiply meter times meter times meter, you get meter cubed. So meters cubed is a unit of volume. It's derived from the unit meter. Other volume units are liters and milliliters, which are smaller. And those are typically used for measuring the volume of liquids. Just like in the English system, we use things like gallons for milk and cubic yards for like steer manure for the garden, right? You can say, I want 5 gallons of that, please. Oh, what to say about this one? Well, the volume of a cube is equal to whatever the edge length is, cubed. So here we have 10 cubes on this side, and 10 on that side, and 10 this way. So 10 times 10 times 10 is 1,000. One of these is 1 centimeter on a side. So the volume of that is a cubic centimeter. And this would be 1,000 cubic centimeters. So 1,000 cubic centimeters. Cubic centimeter has another name. It's milliliter. In medicine, they call it a cc for a cubic centimeter, but we're not doctors. We're scientists. So a cubic centimeter is a milliliter. So 1,000 cubic centimeters is 1,000 milliliters. What does milli stand for? 1/1000th, or 10 to the minus 3. So what this is 1,000 times 10 to the minus 3. Oops, I didn't want to write the milli again. Liters. That is 10 to the 3 times 10 to the minus 3 liters. That's 1 liter. A liter is 1,000 milliliters. If that didn't make sense to you, that's fine. It's kind of lame. This is a very useful table from your textbook. I know on, I think it's the yellow sheet, there's all kinds of conversion factors. You don't need most of those. Google will give you conversion factors. I would advise against using Google to do all your unit conversions because Google will not be with you on an exam, right? And there are some things that Google can't do. Like Google will not translate grams of oxygen into grams of hydrogen based on a specific chemical reaction. But learning how units can work, we can do that quite easily. So some of these early problems, yeah, you can get Google, you can look things up and just get the answer, but you won't be learning anything. So try to just use these guys. You don't need to memorize all of those. This is one that we often overlook that's not listed on the table. A cubic centimeter is the same as a milliliter, just a different name. It's like a nickname. And of these Most of these are giving us relationships between English and metric, like feet and centimeters. So most of these are not exact, but this one is, an inch to 2.54 centimeters. Density is another derived unit. Density is the mass of an object divided by its volume, or D equals M over V. Common units for liquids would be grams per milliliter. Common for solids would be grams per cubic centimeter. For gases, it's usually grams per liter because they are so much less dense. Density is a physical property. This is going to come up in a lab within the next couple of weeks. Density is a physical property that depends on temperature. So density has the mass and the volume. Does the mass of an object change with temperature? No. Mass is amount of stuff. That doesn't change when you take it to the moon. It's just the same. What about volume? Can volume change with temperature? Yeah, it can. You ever had a water bottle freeze and blow up, right, in your freezer? Or something get really, really hot and get all bulgy? So it's not a huge change, but the volume can change a little bit with the temperature of the object. So that means that density, it will be a little bit different at different temperatures. So when we look at a table like this is giving us densities at 20 degrees Celsius. Now, if you're close to that, like 25, 30 degrees Celsius, these are probably just fine to use. If you're like at 100 degrees Celsius or like, 5 Kelvin, then you probably need to look it up because it might be different enough that it'll matter. So this is a table from your textbook that you may need to refer to. On an exam, if you needed any of these densities, I would give them to you. But in the homework, they're going to expect that you go look them up. They're not necessarily going to just hand them to you. The only one that you should even try to memorize is water. The density of water is 1 at 4 degrees Celsius, 1 gram per cubic centimeter. Does that seem a little bit too convenient? The density of water is 1 because the gram and the cubic centimeter or the milliliter were defined in such a way that the density of water was 1. It's not a coincidence. So sometimes you need an estimate for the density of a water or an aqueous solution. And so if you don't have any other resources, just use 1 gram per milliliter. More properties. Intensive and extensive. So intensive, I think of this as like intrinsic. It's part of what the object is. And extensive is more external. So an intensive property doesn't depend on how much of the substance you have. So if you take, you measure the density of water, does it matter if you have a small cup of water or a bathtub of water? No, the density's the same. The color's the same. The melting point's the same, right? It doesn't depend on how much. But what about the mass of the water? The mass of a cup of water is going to be much smaller than the mass of a bathtub of water. Mass is an extensive property. It depends on how much of that substance do you have. So mass, length, volume are extensive properties. This is not a big deal. Intensive properties can be used to identify substances. So here's another one of those story problems. This involves a guy and his fiancée. So You should always read the whole story. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? Does it mention density? Well, I guess it does mention density. It says, he is just determining its density. And it tells you what the mass is and what the volume is. It never says, you determine the density, you compare it to the density of platinum. It kind of leaves you to figure that one out for yourself. So we have the mass and the volume. We can figure out what the density is. We can calculate that. So the density is equal to the mass divided by the volume. So the mass says mass of 3.15 grams. Always write your units. The volume is 0.233 centimeters cubed. And so I'll take the 3.15 and divide by the 0.233. And I'm going to write down the answer. That's what my calculator says. The units are not going to cancel out or anything. They're just going to sit there. Grams per cubic centimeter. Like I said, we snuck ahead and looked at sig figs so we can practice our sig figs here. How many significant figures should this answer have? 3. We're doing division, so we're counting number of sig figs. The mass and the volume, both 3. So this should be 3 also. So we should report this as 3.5 grams per cubic centimeter. How do we know what the density of platinum is? We look it up in the table. Let's see. 21.4. Is that close to 15? No, it's not. So it's not a platinum ring. So the woman in the example is shocked that the ring is faked. She got tricked. She returns it. She buys a new one. The new one has a mass of 4.53 grams, a volume of 0.212. Is the new one platinum? Well, we're going to just do the same thing again, right? Density is equal to mass over volume. 4.53 grams is the mass, divided by 0.212 cubic centimeters. 4.53 divided by 0.212. I lost my decimal point there. 21.3679. Now, some of these numbers in the calculator, they go on with lots and lots of digits. So once we start to get the hang of sig figs, as I'm writing this out and I'm thinking, dang, when can I stop? Well, let's think about it just for a second. 3 sig figs, 3 sig figs. I need to keep 3. So I'm going to keep the 3, and my advice is to write down the next 2. Just write down 2 more in case you need to use it in another calculation. So I've got more than that. I can just stop here. And so that would round to 21.4 grams per cubic centimeter. Is this one platinum? Yeah. Any questions? Yes?
In the exam, if the question does not specify if it's a sig fig or not, do we have to put in a sig fig?
That's a good question. So, on an exam, do I have to get the sig figs right on all my questions? Right? That's basically what you're asking. Is it going to? Yeah. Okay, so on the first exam, there will be problems that are specifically testing you on significant figures. And so there, the whole point is the correct number of significant figures. The rest of the problems, and really most of the rest of the semester, if you're close, it's usually pretty good enough, right? So on the multiple choice portion, like this one, you come up with this in your calculator, but 21.4 is one of the choices, and all the other choices are really different. And we need to understand, there's uncertainty in measurements, and 21.4 and 21.3679 are essentially the same. And so you need to be wise enough to choose this when your calculator shows you that. Okay? So we're all going to give sig figs a shot, but I know some of you will end up just deciding no. So what can you do? So here's cheating for sig figs. Most of the time, the number of sig figs will be the same as the numbers that they give you to start with. Most of the time. Monday night we did some of those with mixed adding and subtracting, and those were intentionally tricky. Not the adding, subtracting, and multiplication, division. Those were intentionally there to trick you, to see if you're doing it right. Most of the time it doesn't end up like that. Another thing you can think about is round everything to 4 sig figs. 4 is usually pretty good. And then it's always better to have too many than not enough, especially in lab. When you do your lab calculations, a mistake that some students make is they'll round everything way too much, and then you end up with data that's meaningless. So when in doubt, write some more digits. Any other questions? Mm-hmm. So this is a thinking question, conceptual. The density of copper decreases as temperature increases, which is common to many things. The density goes down when the temperature goes down. Which change occurs in a sample of copper when it's warmed from room temperature to 95 degrees Celsius? Does the sample become lighter? Does it become heavier? Does it expand, or does it contract? Right here, expand. It's expand. So lighter and heavier would be changing the amount of substance. The mass of an object does not change with temperature, so we should rule those out. So those are not right. Sample expands. This means volume is getting bigger. Sample contracts. Volume is getting smaller. Density equals mass divided by volume. So it says the density decreases when the temperature increases. So it's going from room temperature to 95. The temperature's increasing. The density is going to go down. And so what change in the volume would make this a smaller number if this was bigger, right? Any questions?